Hey everyone, today we're going to continue finding solids that are formed by revolving curves around the x or y axis, but today we're going to add a little twist to this. So in the past couple days we've been looking at curves. When we revolve them, they're just solid figures, but the ones we're going to be creating today are actually going to have holes in the middle. And so that's going to mean we have to treat this integration process a little bit differently. The basic idea is going to be the same, but we have to account for the hole that's created. So, just like it says, sometimes we're trying to find the volume of a solid that has a hole in the middle. So when we have a solid with a hole, we will still use integrals to find the volume, but we will need to take away the volume of the hole from the overall volume. So to do this, we're going to set up two integrals. So we're going to treat it just like before. We're going to have pi times the integral, and I'm just going to say the r in terms of x. So radius in terms of x squared. So there's our pi r squared, our area formula, and you're using our integrals to add up the area of those circles. But we're going to subtract out this integral, and we'll talk about the difference between the big R and the little r in a minute. Okay, so here the big R is what I'm going to call our outer radius. And we'll talk about, when we do some problems, we'll talk about what that outer radius is. And then the R is our inner radius. So essentially, this integral here is just taking out the volume of that hole. Now, one thing I want to bring up is if I have these two integrals, I can combine that into a single integral, which is just pi times the integral of my outer radius squared minus my inner radius squared, and that's with respect to x. Now, obviously, this will only work if I'm revolving around the x-axis. If I revolve around y, obviously all of these are going to be in terms of y. So let's take a look at a problem and really see where do these big R's and little r's come from. So our first problem here is asking us to find the volume of solid of revolution formed by rotating the finite region bounded by the graphs of y equals the square root of x minus 1 and y equals x minus 1 quantity squared about the x-axis. So the first thing I'm going to do here is just draw a picture to figure out what this region is. We always need to identify our region first. So let's see, I'm going to have the square root of x minus 1. So that's going to be my square root shifted over 1. So here, and then 2 is going to be at 1. So it's going to look something like this. So here's my y equals square root of x minus 1. And then x minus 1 squared, that's my parabola shifted to the right 1. So it's going to be this point and this point. So if I'm talking about the region formed by the region bounded by the graphs of square root of x minus 1 and y equals x minus 1 quantity squared, I'm talking about this region here. And since I'm rotating about the x-axis, I'm just going to draw in my top to bottom. So that's the region that's going to be rotated. So just to kind of give us a picture, you don't have to sketch these in, but I'm just going to do this so we kind of get an idea of what this solid would look like. If we kind of think before about reflecting that, right, what I've got is kind of circles. So here's a big circle for my outside, and then I'm taking away the volume on the inside. So you can kind of see how that would generate a 3D solid for us. So here's how I approach these problems. I'm going to sketch the region again where I've got a little less going on, so it's a little easier to see. So I'm focusing here. So I know I had this piece here and then this piece here. So here's the region that I'm revolving. Now, we just talked about there's two things that we need to identify. We need to identify our outer radius and our inner radius. So I'm going to use capital R and little r. And here's the idea. What I like to do with these problems is I always underline the axis that I'm revolving about. I underline it, and then I'm going to draw this in the same color. And I think this really helps you to see why we have that hole. Because you'll notice if I'm revolving this region, right, I'll do this lightly, you can see I have this negative space between that region and the axis. And that's what's going to create the hole in our three-dimensional solid. So my R is going to be the outer radius. I'm going top to bottom. So the top is always formed by this curve here. There's my big R. So from the very top to the axis that I'm revolving about. My little r then is going to be from this curve down to the axis. So essentially it's that negative space there. So now really we're almost there. We just need to define what our big R and little r are with respect to x, and then we can integrate. So for my big R, the top here, that was my curve square root of x minus 1. So that was my top. And then I know I need to subtract the bottom. Well, since the bottom is just x-axis, my bottom is 0. So my big R is the square root of x minus 1. For my little r, now I know the top of my little r is my x minus 1 quantity squared. Again, the bottom is still just 0, so little r is x minus 1 quantity squared. So now we've really got all the pieces that we need. So we're going to integrate. Our volume now is going to be pi times the integral. Well, my limits of integration are going to be my x values. So for this problem, it's from 1 to 2. And then I'm going to do my big R squared. So I'm going to put this here. So it's the square root of x minus 1. And I know I need to square my big R. And then I'm going to subtract my little r, and we'll have to be careful with our parentheses here. I'm going to subtract my little r squared, and then I'm going to integrate with respect to x. So again, this is just my big R, and I square that, and then I subtract my little r squared. And from here, I'm just going to use my calculator. Now, we could have a decimal answer, but again, I'm going to use my calculator to get this exact. So for the moment, I'm going to leave out the pi. So I'm just going to integrate here, and I'm going to be really careful with parentheses. So I'm going to do math 9. I'm integrating from 1 to 2. So now I'm going to do parentheses, square root of x minus 1. Close those parentheses. I'm going to square my big R, and then minus. Now here I know I have x minus 1 quantity squared. I'm going to close those parentheses and square that quantity. And now I'm integrating with respect to x. So I'm actually going to get 0.3. This is an easy one to work with. So I know 0.3 is 3/10, and then I'm going to multiply by pi. So the value of my integral is 3 pi over 10. So really, once we've identified our radii, it's just a matter of doing the integration. Okay, so let's take a look at another problem. This time we're going to revolve about the y-axis. So I actually want you to change number 2. Okay, we're going to find the volume of the solid of revolution. That just means we're revolving about an axis. We're rotating this region bounded by y equals square root of x and y equals x cubed. And again, I want you to change that to revolve about the y-axis. So first thing I'm going to do is graph my two functions. So y equals square root of x, I know is going to look like this. Let's see, square root of x, so 1, 1. So I kind of went off here. All right, so there's my y equals square root of x. And then I know this goes through negative 1, 1. I'm going to graph my y equals x cubed, which is going to look something like that. So you can see now, here I have this region here. And since I'm going about y, I make those perpendicular to y. So if I revolve this around y, can again kind of just sketch this out here and draw in some circles. All right, so I've got this outside region, and then I'm creating this kind of hole in the middle here. So again, I'm going to draw just another sketch of this so I can more easily identify my outer and my inner radius. So I know I'm going from 1 to 1 here. I have a piece that looks like this, and then I have my square root of x that looks like this. Now, we said we're revolving about the y-axis, so I'm going to do that in blue. That tells me kind of where my boundary is. So now, about the y-axis means I'm going from right to left. So now my furthest most point over to my axis is going to be from here to here. All of that space. And again, my little r just kind of accounts for this negative space between the axis and that region that's being revolved. So I have one more thing to do. Since I'm going around the y-axis, I need my function solved for x. So if I have y equals the square root of x, I know my x is going to be equal to y squared. And then for my other one, I have y equals x cubed. So x is just going to be the cube root of y. So now for my big R, right, now we're doing right minus left. Well, my right was my x cubed, so my right is going to be my cube root of y. My left is the y-axis, so that's just minus 0. So my right is the cube root of y. For my little r, well, my right, that was my square root of x, so I know that's y squared. Again, my left here is the x-axis, or excuse me, the y-axis, so that's just 0. So I have y squared. So now I've got all my pieces, so I know my volume is pi times the integral. Now my limits are going to be the y values here. So I'm going from 0 to 1 of my big R squared minus my little r squared, and I'm integrating, with respect to y. So my big R, we said was cube root of y, and my little r was y squared. Okay, and so then again, we'll use our calculator to calculate that. Let's see, we're going to do math 9. If I push this up here, maybe I can show both. Okay, integrating from 0 to 1. So y, I'm going to do x to the 1/3. And I know I need to square that. Minus, well, x squared squared is just x to the 4th dx. Let's see if we can. Okay, that's not going to turn into a fraction, so now we'll just multiply that by pi, and we get an answer that's approximately 1.257. All right, so those are pretty straightforward examples there of just revolving around x and y. Okay, but again, creating that hole by that negative space between the region and our axis. Now we're going to look at a couple different axes that we really haven't looked at so far. So we're going to be working with the solid generated by revolving the region bounded by y equals square root of x and the lines y equals 2 and x equals 0. So that's always going to be our region, but we're going to revolve it around two separate axes. So first we're going to do the line y equals 2, and then we're going to do the line x equals 4. And we'll kind of see how that works. So let's see, we'll do y equals -2 first. So I'm going to sketch this out. I've got y equals square root of x. So here's my y equals square root of x. And then, let's see, by revolving the region bounded by y equals square root of x and the lines y equals 2. Okay, so I've got y equals 2, y equals square root of x, and then the line x equals 0, or our y-axis. Okay, So there is our region. Now, we're going to rotate it about the line y equals -2. So just like I was doing before, I'm actually going to draw that in blue. So now my axis that I'm revolving it around is something other than the x or y axis. Now, since this is parallel to the x-axis, I know that I'm going to integrate with respect to x. Okay, so I'm really looking at here, top minus bottom. So now I just have to establish my big R and my little r. Well, we said if we're doing top minus bottom, my big R is the very top, and it goes all the way down to the line that I'm revolving around. My little r goes from this curve, and again, all the way down. So now we just have to be careful because now our bottom isn't 0 anymore. If I look at my big R, it's the top, which in this case happens to be the line y equals 2. So I have 2 minus. My bottom now is the line y equals -2. So I have 2 minus a -2. So my big R is just 4. My little r, well, this curve now is the square root of x. And I'm going to subtract, again, the bottom, which is -2. So my little r is the square root of x plus 2. So now to find the volume, again, we're going to go to our integration here. It's pi times the integral. Well, let's see. I need to find out where the square root of x is equal to 2 to find that intersection. So if I square it, I know x is equal to 4. So I'm integrating from 0 to 4. And again, I'm going to have my big R squared minus my little r squared, and I'm integrating with respect to x. So the big R we said was 4. My little r, I didn't leave quite enough room, is the square root of x plus 2. Okay, and I'm just going to put that in the calculator. So second pi math 9 from 0 to 4. 4 squared I know is 16, so I'll just simplify that. Minus, I have the square root of x plus 2 quantity squared, and I'm integrating with respect to x. Okay, and I get a volume of 58.643. Okay, so for the last problem here, now we're going to do the same region, but we're going to revolve it about a different line. So I'm going to draw my picture once more so I can see this. And here's my line y equals 2. But now I'm revolving about the line x equals 4. So now, since I'm revolving about a line that's parallel to the y-axis, I'm going to integrate with respect to y. So it's going to look like this. So now, if I'm integrating with respect to y, I know my radii are going to go from right to left. So here's my big R. And then again, my little r just accounts for that negative space in between my region and the axis that I'm revolving about. So I'm going to make a note here, right? We're going to be right to left. So for my big R, my right is 4. My left is just the y-axis, so that's minus 0. So my big R is 4. Now, my little r here, I guess, let's see. For my little r, my right is still 4. Then minus, well, I have to use this curve with the square root of x, but I know since I'm integrating with respect to y, I have to solve that for x, so x equals y squared. So my little r is going to be 4 minus y squared. And again, now we can do our integration. I'm doing pi times the integral. My limits are the y values, so I'm going from 0 to 2. And I'm going to do my big R squared minus my little r squared, and I'm integrating now with respect to y. So my big R is 4. My little r is 4 minus y squared, and then we go to our calculators. So second pi math 9 from 0 to 2. I have 4 squared is 16 minus, I have 4 minus x squared. I'm going to close that off and square that radius. Move this over. I'm integrating there, and so I get 46.914. So that is it. So again, the big difference today was the holes in these solids that was created by this negative space. So now, as we go forward, by the way, I should have said, we call this the washer method because of that hole in the middle. As we go forward, you're going to have to be able to differentiate between the problems that are just disks, so they're solids when they're evolved, versus the ones that have holes that are in the middle. And you'll see those as we go through the next practice.